Mineralization from organic fertilizers and compost. So let's get started. So the outline of my talk, first, very basics. Why nitrogen? And nitrogen in plants and nitrogen in soil, and plant available form of nitrogen in the soil. Then I'm going to talk about nitrogen mineralization versus nitrogen immobilization. Those are very important principles when you talk about nitrogen management in organic systems. And then finally, main topic, nitrogen mineralization of organic fertilizer and compost, incubation studies, and simulation model. That's the outline of the talk. Let's get started. So nitrogen, why nitrogen? Nitrogen is important, key to crop production, because plants need nitrogen for multiple functions: photosynthesis, biomass structure, metabolism, energy production, reproduction. Every process needs nitrogen. So when nitrogen is deficient, plants tend to have yellowish green leaves because of the lack of chlorophyll, and smaller plants and lower yield. And then, but you have excess nitrogen, plants tend to have darker green leaves, large vegetative plants, and sometimes become susceptible to diseases too. How about in the soil? Nitrogen in the soil can be divided into organic nitrogen and inorganic nitrogen. And inorganic nitrogen is mainly ammonium nitrogen or nitrate nitrogen. Typically, about 98% of total soil nitrogen is organic form, and only 2% is inorganic form. The bad news is the 90% of organic nitrogen is not plant available form. Only 2% of inorganic nitrogens are. Note that the plants can absorb small amounts of organic nitrogen, and some crop plants can do more than others. But the good news is a small portion of organic nitrogen can be turned into inorganic nitrogen through the process called mineralization. And first to ammonium. And then ammonium can be turned into nitrate through the process called nitrification. Both mineralization and nitrification are biological processes. Therefore, it can be affected by environmental factors such as soil temperature and moisture, so forth. I'm going to talk about it more in a minute. Also, this ammonium and nitrate has different charge. Ammonia has positive charge and nitrate negative. This has very important implication too, because majority of soil particle has negative charge. So ammonia can be absorbed and can be held and then retained the nutrient, nitrogen nutrients, but nitrate having negative charge, it repels to soil particles. So it moves, nitrate moves along with whatever water goes. It soluble in water and move with water. So nitrate is leaching, much more leaching susceptible compared to ammonia. Nitrogen mineralization and immobilization. Soil microorganisms decompose residues, but need nitrogen and carbon as building blocks for their own biomass. And the carbon is also used as an energy source. And nitrogen mineralization is the release of excess nitrogen in the form of ammonium into soil solution. Whereas nitrogen immobilization is uptake of nitrate or ammonium from soil solution and incorporation into microbial tissue, so back to organic form. This is another way of showing relationship between mineralization and immobilization. So changing organic nitrogen into inorganic form of nitrogen is called mineralization, and the reverse is immobilization. And the direction is approximately determined by carbon to nitrogen ratio of the organic amendment. And typically, when carbon to nitrogen ratio, C/N ratio, is below 20 or 30, mineralization takes place. But if CN ratio is much higher than 20 or 30, nitrate and ammonia is going to be immobilized back to organic form. Immobilization takes place. This shows the nitrogen dynamics in conventional systems. Crop nitrogen demand is usually fulfilled by synthetic fertilizer or fertilizers, mainly in inorganic form, plant available form. So it can provide plant available form of nitrogen quickly, but if you apply too much, it can cause it might be lost to the environment. Whereas in organic systems, most of fertilizers are provided as organic form. Therefore, it has to go through the extra step of mineralization, or sometimes it can be immobilized, reverse form. So organic systems nitrogen management is inherently more complex and has more time to release plant available form of nitrogen compared to conventional systems. And today I'm going to talk about 3 of those organic fertilizers: compost, solid organic fertilizer, and liquid organic fertilizers. Factors affecting decomposition and nitrogen mineralization. As I said already, environmental factors such as soil temperature and moisture and management, if you apply on top of the soil or incorporate in the soil, that affect the decomposition, mineralization rate of organic fertilizers. Also, quality of organic sources, nitrogen content, C/N ratio, and availability of carbon and nitrogen. So let's get focused on this quality of organic source for now. Daniel Geisler and Patricia Rizeki, my collaborators, did some experiment collecting different kinds of organic fertilizer and examine the mineralization rate of different organic fertilizers under controlled environment. They tested 6 different kinds of material and multiple materials for each one: municipal yard waste, trimming, compost, poultry manure compost, granular fertilizers, and blood and feather meal, liquid organic fertilizer, and guano. And the typical nitrogen contents change from low, less than 1% to high, like 12 to 13%. And typical CN ratio change from, this is high CN ratio, 13-20, to go down 3 to 4. And when these are incorporated in the soil and incubated in ideal moisture condition and ideal temperature, it starts to decompose and release plant available form of nitrogen, inorganic nitrogen. But very depend on material. The composted trimmings, as you see here, there's almost no nitrogen to be released, even after 12 weeks, 84 days. Whereas composted poultry manure contains almost 15% of inorganic nitrogen, plant available nitrogen to begin with, and release a little bit more. At the end, like 30% of total nitrogen becomes plant available form. Granular fertilizers, 4% nitrogen, 20% to begin with, and then release 50%. And then liquid fertilizers and blood and feather meal, almost nothing, or liquid might have 10%. Then 12 weeks later, like 80%. And guano is very different. It has more than 50% available, plant available nitrogen to begin with from the beginning, and then release more nitrogen later. So the total nitrogen content is usually labeled on the back, right? NP2O5, K2O content is on the bag if you buy those things in a bagged format. So that nitrogen content doesn't necessarily mean all of these becomes available in organic fertilizers. For example, liquid fertilizer, let's say 30% total nitrogen content. Based on the incubation study, 50 to 100% become mineralized in 12 weeks. So actual available content is 1.5 or 3%. That's a plant available form of nitrogen in this fertilizer. Some granular fertilizer may have 4.5% guaranteed analysis. That has a total nitrogen 4.5%, but only 40 to 60% becomes available. So available form of nitrogen can be 1.7 to 3%, and so forth. So that's the important point to understand how to use nitrogen, organic nitrogen fertilizer. And then the good news is how much mineralization rate has a very strong correlation with carbon to nitrogen ratio. This is Patricia and Daniel's data. Strong correlation to CN ratio. So higher the CN ratio, lower the nitrogen mineralization. So these are different kinds of fertilizer, but very strong correlation exists. And this correlation was used based on this data. Current Central Coast water quality regulations, Ag Order 4.0, gives organic fertilizer discount factor, because total nitrogen content of organic fertilizer does not necessarily means all of these becomes plant available. So when you report nitrogen input for CN ratio 5 organic product, for example, here, you can multiply total amount of nitrogen by 0.574, because this CN ratio is 5, so like here, so only 60% becomes available. So that is included in Ag Order 4.0 now for Central Coast growers. But there are so many different kinds of fertilizers, even in the same category, like guano and feather meal, poultry manure, compost. There are so many different kinds, and we cannot test all of them. So we collected available data from published literature and then compile to make a simulation model so that we can use it for decision support tool. And then in this case, we collected so many data for different organic fertilizers. And the CN ratio varies a lot, and it has a considerable range within each category. And then Daniel Geisler came up with a simulation model for nitrogen mineralization. And this is an example for guano. Multiple samples collected, but the guano is pretty much the release carb is not so much variable. It has more than 20% of available nitrogen to begin with. That's why it very quickly, it works quickly as almost chemical fertilizers and release nitrogen fast. After 24 days, 20 to 40 days, almost 70% of nitrogen becomes available. Feather meal is a little bit slower and almost no available form to begin with, but after 20 days, 60%, most of them 60% available. One feather meal has a high CN ratio and then much slower, but most of them has like 60% after 20 days. And poultry manure, this is highly variable. It depends on what kind of beddings you use and how much beddings are mixed together. So it, minimum is like only, it has a available nitrogen to begin with, but the slow one only release like 20%, but high nitrogen one or low CN ratio one release more than 45%, more than 40% of the nitrogen. But once composted, the variability reduced greatly. So poultry manure compost reduced nitrogen slowly up to 30% or so in 60 days. The other way compost, this is highly variable too, depends on the material. the composting process, I think. And in this case, a maximum CN ratio 1 is the really slow and almost negative, 2 to 1%. And the minimum CN ratio 9 release like 8% after 100 days. Vermicompost is also variable. Maximum CN ratio 35 is almost 0, negatively immobilizing nitrogen. And then minimum CN ratio is 11, and then release more than 10%. So this simulation model is actually available online. If you type this website, you can use this simulation tool. I'm going to talk about more. And then this is going to be integrated with a crop manage online decision support tool for nitrogen and irrigation management. At this point, crop manage can handle only conventional systems and not in organic systems because there's no simulation model for mineralization. But we're trying to make that happen by integrating this simulation model into crop manage by the end of this year. So please stay tuned. And this Daniel's simulation model assumes soil temperature, soil moisture is the consistent because most of the time when you are growing crops, you irrigate it and keep soil moist. But on top of this different quality of organic source based on CN ratio, this model also will take into account soil temperature difference. But for management, also it assumes incorporation, not the top dressing. And Richard Smith's work shows that if you apply fertilizer not incorporating the soil but applying on top of the soil, mineralization rate is much slower. So that's needs to be taken into account if you apply just the top dressing. So this Daniel's online tool, you can choose regions. I think there are multiple regions, 4 or 5 regions: Sacramento, Central Valley, Central Coast, and the Southern California, so forth. And type of amendment, 7 different kinds: application rate, application date, and period of interest, and the depth of incorporation. And then if you know actual number of amendment you are going to simulate, you can type in 2. Otherwise, typical number is going to be used. And soil properties too, because this can simulate nitrogen mineralization from soil organic matter as well. So this example, 1 ton of feather meal in Sacramento Valley, April application, and there's some data in it. So soil organic matter content is 3%. Then you can get this kind of simulation data. The one thing is you can read like after 50 days, you're going to have 150 pounds of available mineral nitrogen. That's what it says. But the important thing is this doesn't take into account the residual nitrogen in the soil. So it's always good to test soil nitrogen, inorganic nitrogen content before using this kind of tool. And this is an example of different date. Left side is April, and the right side is October, as beginning date. And then pattern is a little bit different. October 1 released more nitrogen upfront compared to April. And this is the different type of things, poultry manure compost. In this case, seasonal difference affect more. April, this is maximum 80, and October only 60, so April released much more. Again, this tool is available online. So what is the release pattern of cover crops? And then how can we synchronize or match nitrogen supply from multiple organic fertilizers with the crop nitrogen demand? And crop nitrogen demands, these are some examples. Broccoli, summer broccoli, and this is overwinter broccoli. And then this is tomatoes, and this is strawberries. Each crop has very different nitrogen demand. So how can we match those nitrogen supply from different organic fertilizer and cover crop with the crop demand, which is very important. Well, unfortunately, we don't have time to talk about it today, but here's an available resource for that kind of next more comprehensive nitrogen management. This in our publication was just released December. If you can click here, click this link, you can download it for free. And also, it's a little bit far from now, but we already chose the date after Thanksgiving this year. Three-day series of practical training on nitrogen planning and management in organic production of annual crops. That's going to happen and covers whole thing, not just mineralization pattern, but how to manage nitrogen and irrigation during this 3-day series. So if you're interested in, please email me or Margaret Lloyd. Margaret is organizing this with us. So to be updated for this event. I thank you. I thank the funding agency, CDFA, Specialty Crop Grant, and Fertilizer Research and Education Program, and my collaborators, Daniel Geisler, Patricia Lizik, Margaret Lloyd, Richard Smith, and Michael Kahn, and my lab staff, Margarita Zavada and Sydney. With that, I'll be happy to answer any questions. Thank you very much.